let's have a little look. Okay, so so this we saw. This was the effective potential with my little mistake. Now I think I have to change something. So that's my effective potential. We've talked about this stuff. We wanted to find those minima, right? We wanted to find the maximum, those flat points in the curve, and then we're going to say, well, what's the limit where we don't get those anymore, where the angular momentum gets so small that we no longer actually have those stable points. So the first thing we need to do is just to differentiate the potential, okay, which is going to give us the positions of those flat bits. Where's the flat points of the curve? Okay, so that's what we've got here. But this is actually equal to derivative with the potential with respect to r is negative of the force at the same time. Okay, so it just amounts to where the force is 0 is where the potential is flat. Okay, so we differentiate our. Oh yeah, I see. As I scroll the page, it leaves the writing behind. That's really useful. That's not quite what we wanted, really. Let me see. Does that one work any better? Does that move with it? No. Okay. Right, I don't know quite what we do about that. Maybe I just keep it still and stop. So anyway, so we differentiate the potential. And so we have an m over r term, which gives us a minus m over r squared here. But the minus in front of that. So this differentiating the minus m over r gives us plus m over r squared. Derivative of the h squared over 2r squared, that's r to the minus 2. We're going to get a minus 2h squared over 2r cubed. The 2's cancel, and that gives us this term. Okay, so we're just differentiating this term by term. This one here becomes that. Minus mh squared over r cubed, so mh squared r to the minus 3 is going to give us the 3 term here, gives us that. The minus, changing it into a plus. Mh squared over r to the 4th. Okay, so that's the derivative of the potential. So first, yeah, this is actually equal to minus the force, and as I said, we've got a 1 over r to the 4th term in the force. So modification of the force. This is the 1 over r squared. This one here is the Newtonian 1 over r squared. Here's the extra term that we've got, 1 over r to the 4th. But actually, what we're trying to do is so we're going to set that equal to 0 and find the positions of these minima. Okay, so when is this potential 0? When is the derivative of this potential 0? When is the force equal to 0? So r squared, r cubed, r to the 4th. We'll multiply the whole thing through by r to the 4th, and this then becomes m r squared. Multiplying through by r to the 4th. This becomes minus h squared r. This becomes plus m h squared. Okay, and so this actually now is just a quadratic formula. Which we can solve for r. Okay, so it's m r squared minus h squared r plus 3m h squared. So there's an r squared term here, there's an r to the 1 term here, and this is just your constant. Quadratic formula. So this is now giving us the radius values at which that potential is flat. Okay, so this is basically the positions of the stable and the unstable circular orbits from that potential. Okay. Where's my